The future is watching. Welcome to Opcode Virtual Summit.
Hello. Well, I hope everything is working fine. If there is any issue as usual, just let me know. This time, I didn't send the mailing list to everyone. So I guess if you're on the stream now, it means that either you're a speaker or you're watching the tweet, or you actually subscribe to the channel. And actually, even if you check on the website now, I moved the oh, that's kind of crap. I was about to say, like, I moved the YouTube view, which apparently, like, the Twitch one only works from time to time. But if you rather be on YouTube rather than Twitch, the link is available on the actual Twitter account. I'm wondering if the view is not working. Yeah, actually, I think maybe it's because in incognito mode it does not show it, actually, because it does work on my regular session. It's good to know. So I hope you're all doing well for this 9th edition, as Sima just reminded us in the chat. Actually, I can probably even show it here. It was hidden. Yeah, so this is the 9th edition out of a series of 10. So in 2 weeks, it's going to be the last edition, I think, at least for that season. Then I will take a break. Maybe I will do something like a bit more casual instead of just like a once every 2 weeks type of thing. So far, after like 9 episodes on YouTube, I think we have like around like 800-ish subscribers. I guess it's an average of like like 100 per episode. But I don't know if we're gonna get to the 1000 by the 10th episode. I guess we will see. And on Twitch, it's even more difficult to get followers, but I think like people are more used to like more regular content. So I guess that's my feedback, as from the actual. Oh, it works fine on your incognito view. Okay, interesting. I guess it's a bit random then, because it says failed to load on my thing. But the great thing is like you can have the chat on the side and stuff. Although like the YouTube one is probably more convenient because unlike gamers, I guess everyone has a YouTube account. Yeah, but it's quite difficult to get like subscribers on YouTube and Twitch compared to Twitter. Although on Twitter now, I guess it's also becoming like more difficult than before because there's so many people. And I think there's also like less viewers now because like confinement is being lifted in a bunch of places. For instance, us in Dubai now, like the confinement is like very limited. We just have to wear a mask when we go outside. I think something in France, I don't think there's like a really enforced like confinement unless you're traveling or coming inside the country. But yeah, so thanks for joining us for this 9th episode. I think Jaziel, you're one of the like strong supporter. I think you've been here from if probably like the first or like the second episode, and you've been attending all of them. Thanks for the support. It's quite nice. Yeah, that's always good to see. I do think like the format though. I do like the format. I would say I wish like more people would like benefit from it, because I don't know, like in terms of viewers, it's not doing that much. I would say like regular like webinars and I don't know, like ransomwares would like probably do like more views, maybe because it's more accessible, So I'm wondering if like the content is like too niche or not, but at the same time, I would say that's what brings like a quality audience, which is quite good, especially like nowadays, I would say. And the flexibility I think is kind of cool. Like so I was talking with Mohamad, who's gonna speak after on malware HTTP communication channels. And for instance, like he said, he prepared slides. He has a white paper that he's gonna publish after, so we're gonna put it on the GitHub. So that's quite cool. And Patrick is gonna come with like his blog post and read the blog post, which is also what I did last time when I made my GitHub repository public for my ARM64 like exploit. So I think it's kind of cool to have like a more like flexible format, because I don't know if any of you remember, but every time we had to submit something to a FRAC or people wanted to submit to a FRAC, you never knew when was going to be the next edition. And then at some point, like, which is not a bad thing, you know, they kind of were a bit more like picky on the type of writing, and, you know, they wanted it to be like a bit cleaner, which, like, knowing the backstory, you know, it definitely makes sense because of all the stuff they had. But yeah, I think I still like the format of like, okay, if you have something cool, you can present it, you know, whatever format you like. Let me know what you think about the format, and what could also be done for the last Opcode Live, which would be on July 29. So in 2 weeks. I think we're probably gonna have like 1 or 2 roundtable, maybe like at least 1 talk. And if there is more stuff like coming up, you know, like we'll probably just like add it to that one, I guess. But yeah, if there is like anyone you would like to see or stuff you would like to have presented, yeah, definitely let me know for that last episode, which is like in 2 weeks. I guess it's gonna arrive soon, because if you think about it, the first upcode I think was like 25th of March already. So I guess it has been like 4 months already. So it does go back like very quickly. And yeah, and since life is going back to normal now, so I don't know if it's still worth like continuing the thing or not. Definitely let me know. Anyway, like as I was saying, we're always on the Discord channel, so definitely more than happy to hear more feedback around it. But yeah, so without further ado, because I think I've said all the stuff I wanted to say for that time, definitely come subscribe if you didn't yet, you know. So you cannot subscribe. Say like 8:30. So all the presentation are still here in case you missed any of the previous editions. So as usual, you know, we take the live stream and then we cut it, do some cleaning, put all the content here. Definitely in 4 months, definitely got more content than in 3 years of Opcode, I would say, because yeah, I guess that's like 10 editions, like between 3 and 4 talks every time. So that's between 30 and 40 talks. I guess that's the equivalent of like 2-3 conference. So that's pretty good. Definitely thanks to everyone who has been speaking, and even we've had some returning speakers. So Costin was the main returning speakers at some point, but for like this episode, it's kind of cool. We have 2 returning speakers. So we have Mohamad and Patrick. So yeah, that means a lot, because it also means like speakers also having a good experience, enjoy the format. And I personally also, as like a speaker, I do think it's much better because you don't have to wait. For instance, like what I was presenting last week, there's some research I did 2 weeks prior it. Then as soon as I was done, I just presented it, and that's it, you know, with my blog post. Otherwise, you would have to wait like 3 months to be accepted in a conference. So I do feel like it's definitely more efficient as a medium to share the data or information. And we're probably going to see more of it. So, but the main people who I've seen who are doing some pretty good streams were all the bug bounty people. Super active on Discord, super active on Twitch, and people are like yeah, really active. So I don't know if this is because it's less niche than that. Also, I'm definitely sure they're making a much better job at promoting, because it was not really the priority. Like, also the idea is to also grow organically, without pushing too much on getting like additional viewers to see how organically it could be done. But yeah, they've done it like pretty well. Other than that, all the people doing like virtual conferences so far, I mean, I'm sure you would all agree, like over the past 4 months, I've seen a lot of those virtual events. It was a bit too much. I mean, it is still too much, like there's something like almost every day. A lot of stuff is not really, I would say, not really relevant. And whenever there's like some cool stuff is like really late. But yeah, so yeah, so without further ado, I will let Mohammed get ready, so you can share your screen and everything. And yeah, so we can hear I didn't check the slide, although I received them in advance. I just wanted to get the surprise for it, so I can ask the questions at the same time as I am watching the presentation. But yeah, so he's gonna be talking about some new malware. I don't know if this is one malware or collection on malware using similar like communication techniques. But yeah, that should be quite cool. So I'm just gonna launch the transition and then we can go.
The future is watching. Welcome to Opcode Virtual Summit.
All right. Hi, all. Can you hear me, Matt? Yep, awesome. So, okay, my name is Mohamad Mokbel. I'm a second-time presenter at Opcode. It was too good first time not to do it another time with another research. Today, yeah, no, I won't. That's okay. It is too tempting to do it, but last minute decision not to do it.
Yeah, that's fine. That's fine.
No worries. So today I'll be talking about a journey into malware HTTP communication channels spectacular. It's a journey, meaning that it's based on my own experience, like at least for the last 10 years, in reverse engineering different malware communication channels, client and server-wise. And in particular here, the focus is on HTTP, not HTTPS or any other custom protocol, be it ASCII or binary. So it's going to be interesting, and I'm pretty sure that you will see stuff that before, at least this is my expectation. You might have seen like blogs here and there talking about some of the stuff, but definitely not to the depth that I'll be going into, and this particular research. And to mention it, like right at the beginning, there will be a full technical paper talking about everything that I'll be talking about in this presentation. So you don't have to worry about taking notes or scratching your heads or whatnot. The technical paper goes into full details into every case that I'll be addressing in this talk. So a bit about me. I'm a senior security researcher at Trend Micro. I'm a member of the Digital Vaccine Lab. If you haven't heard of us, we do, it's part of Tipping Point, and we work on IDS/IPS solution. We write filters, reverse engineer malwares and vulnerabilities. And my interests lie in the area of reverse engineering and malware research, intrusion detection and prevention systems, and I have a special interest in C++ language, and in particular the compiler and software development and performance analysis. And as you can tell from the talk, I'm also interested in exotic communication protocols, not only specific to malware, but communication protocols in general, so I have a bit of a critical mindset when it comes to reversing protocols or even just reading the specifications. So I like to dabble into this area as well. Introduction. So as I mentioned at the beginning, oh, yeah, gotcha. Okay, for the introduction, as I mentioned, the talk will be about malware communication protocols. And I know you must have reverse engineered malware CNC communication channel, or if you read a blog post or whatnot. At the end of the day, once the malware is in the wild, its goal is to reach out to a command and control server to receive commands, exfiltrate data, and do whatever nefarious activities on the infected system. That's the whole purpose of having a CNC channel. Now, it could be using either a TCP layer or UDP layer, depending on the protocol, and be it like a custom or a standard protocol. On TCP, you could be using, for example, IRC, SMTP, FTP, HTTP, HTTPS, SMB protocol, DNS, ICMP, SSL, or TLS. Of course, malware could use like any other protocol. It's not specific to those that I'm just listing. But those are standards, and the malware could leverage them easily without having to innovate on coming up with their own custom protocols. Now, this is an example that shows how a custom protocol that is ASCII-based is constructed at the packet level. For example, we have this packet, which consists of the following pipe delimited data. It is very simple. First, we have, for example, the word God, which is could indicate a magic string. It's used like as a unique identifier that the malware server would be expecting when the malware sends this request to the server. And then followed by the infected system OS version, then the pipe character, then the host name of the infected system, then the username of the currently logged in account, then followed by the OS bitness, be it 32-bit or 64-bit. So this is a very simple ASCII-based protocol that a lot of malware use when they want to fingerprint the infected system and send such a packet to the backend server. The other example is also a custom protocol, but is binary-based. And one of the most famous custom binary-based protocol is the one used by PCRAT, which is also known as GhostRat, although it's not GhostRat, it's just that the magic byte is set to the word ghost, but there is no rat known as GhostRat. This is the source code is open source, and the original name of the rat is PCRAT, just to set this straight from the beginning. And the structure of this packet in binary format is as follows. First, you have the first 5 bytes. It's in hex. And they have the word PCRAT in ASCII. So this is a unique identifier that you set at compile time when you want to generate a malware sample via the builder of PCRAT. And then what comes after is a double word value that would indicate the packet size. And then another double word value, which indicates the size of the data that follows, but before zlib compression. And then what follows after that, for example, you have the 789C is the header for the zlib compression library, and then the zlib compressed data. So this is a perfect example of how a binary custom protocol looks like. And this is not like unique in any form or shape. Many other malware custom protocol follow similar pattern as well. You will be surprised to see that such a pattern also exists with other malware families too. They might have a byte here, byte there, that would indicate different flags depending on the malware configuration. But at the end of the day, they all sort of follow the same structure. Okay, so also we're still in the introduction section. So at the beginning, you must be aware, back in the days, IRC was sort of like the de facto protocol for malware. Why? Because it was very easy to just set up an IRC server and have your malware communicate with it without having to invest into setting up the back-end component to communicate with the server. So you have this one standardized, ready-made for you IRC server where all your bots can communicate to that channel and be instructed remotely in a very easy and organized way. But then you have all of these corporations started blocking IRC protocol, right? And it's very easy. You can either block it at the port number or at the semantic level of the protocol via an IDS signature or IPS signature. And then it becomes an issue for malware authors, right? Despite how easy it is to use it, but it's no longer effective to be used in the wild, since blocking it became like a standard policy for all these major corporations. So they started shifting into HTTP protocol, which becomes the standard for malware CNC communications, because it's also, at the end of the day, it blends with the normal traffic. So there isn't much difference between normal traffic and malware traffic, unless you do your reverse engineering work and to figure out what is benign and what is malicious. And HTTP, I'm pretty sure you're all familiar with it, is text-based protocol, extremely simple. Well, simple is again is a relative term. Depends on how much you read into the specification, especially when it comes to implementing the actual HTTP protocol in terms of parsing it. So that's why the focus is on HTTP and not IRC or any other protocol. This is, like I'm mentioning, what I'm about to mention next is, I know it might seem very straightforward or very obvious for some of you, but considering my experience in some teachings at some corporations or even like talking to some friends about some of this stuff, it might not be obvious for them, especially if you don't have a background in software engineering or in implementing your own protocol or coding your own TCP, UDP level type protocols, or even HTTP. So these things might seem alien to you. Again, just to mention, a protocol is never defined by its port number. It's just a port number. This is part of the standard. It's a default number. Again, I understand some protocols other than HTTP, they might have a specific port number that you cannot change, but still, a protocol is never defined by its port number. You can change it at will, as long as both the client and the server understand it, then that's fine. It is actually the semantics and the architectural design that defines a protocol. You have to adhere to this grammar. Otherwise, it's not really the protocol that you're talking to. Now, the other misconception is when it comes to Windows, and in particular using either of the libraries, WinHTTP or WinINet. So we use these libraries for sending HTTP request to the server. That there is this misunderstanding that if I'm using these libraries, this means that the generated request must be HTTP RFC standard compliant. It's not really the case, because it all depends on the implementation of how these libraries work. And the other thing is, if you're using Windows socket WinSock library, for example, because you could send a custom TCP packet with this library, or you could construct your own HTTP request, like statically or dynamically. You can have the entire request hard-coded or dynamically fill all of the parameters in the request. In your code, you would have to set everything like by yourself, starting from the HTTP method to the HTTP version to whatever header you reference. But if you're using this library, it doesn't mean that you're not using HTTP protocol. Again, it's not the library that defines the protocol. It is the protocol semantics itself, and of course, whatever the server is expecting. And the other notes that I want to mention is that malware has full control over the client and server setup, which is fundamentally different from using a web browser. A web browser would have to be almost, depending on the company, 100% HTTP RFC compliant to communicate with different HTTP servers. Whereas for malware, no, not really, it need not be the case. Although you might see HTTP traffic on the wire generated by malware, but it need not be HTTP at the same time. And the whole purpose of that would be to camouflage the actual custom protocol that they are communicating with the server within HTTP traffic. So just because you see some HTTP elements in the traffic, it doesn't mean that it is HTTP traffic. So just keep that in mind. We'll see later on in through the cases that I'll be going through. So, as I mentioned earlier, HTTP is becoming the de facto protocol for malware CNC communications. And in doing so, it happens that these authors, they committed some interesting mistakes, or I should call blunders, and be it intentional or non-intentional. And this is what makes it interesting, actually, that we don't know if it is intentional or not intentional. For example, you have specific headers in a GET request that only make sense in a POST request, like at the protocol specification level. So you might be wondering, so why would the author use such a, like, why would the author commit such a mistake? Sometimes it's obvious, sometimes it's not. Sometimes you can clearly say that, oh, it's a blatant mistake by the author. He doesn't know what he's doing, just like lots of senior software engineers. And then you also have using wrong content length value that doesn't match the actual payload size. So what's happening here? If this is the case, and yet I'm getting a proper HTTP server response, yet the request is not valid, so you might be wondering, is the server backend really HTTP server if it is really like vetting the actual request specification? So those mistakes are interesting in their own, actually, because sometimes you have malware traffic that's not easily filterable via an IDS signature, be it for potential false positive, or it might incur a lot of performance impact. So those blunders and mistakes in the request or response of the server, we might leverage them for our own advantage and write IDS, IPS signature to detect them. So in the rest of the talk, we will go through this journey of documenting such semantic and syntax level type errors. So it's not only typographical. It's not like you have you see this and written in that as that. No, you will see semantic type error as well as syntax level errors. And just before I continue, I just want to mention this, that since I'll be putting a lot of packet captures, HTTP requests in particular, I just want to mention that the value of the host header field in all of the packet decodes, I've replaced them with the value example.com, since I don't want to mention the actual domain name. And in case it's an IP address, I replace it with 10.10.10.1, unless otherwise noted. So, and also just to mention that all of the malware that I'll be talking about here, in the appendix of the paper, I have all of the MD5 hashes, as well as the malware family name reference as well. So you can look them up yourself, and they should be available on VirusTotal. So there's no secret here. You can verify everything I say here. So there's a difference of between coming up with such scenarios versus having something in the wild making such mistakes. So thus, like the proof of this work. So first, we'll start with the first case of a malware known as PKey or Adelinok. Adelinok, depends whichever way you pronounce it. In this particular case, we have the scenario where the content length value does not match the actual payload size. As you can see in the request, the content length value is 4, yet the payload size, here the payload, which is shown in hexadecimal, is actually 271 bytes. I'm not showing all the payload size because it's irrelevant. It's only the first 4 bytes, or in ASCII, translates to PKey value. So how come this discrepancy? The content length has to hold the value of the payload of the post request, and yet there is no match here. So what happened? What went wrong? How did this happen in the first place? So it is such a blunder that I'm talking about. So in case you're wondering how the malware does it when it comes to calculating the size of the entire packet, this is what it does. So first, it initializes a buffer to 0, like the buffer is initialized on the heap, the size of 431 bytes. And that buffer is set to 0 initially. So the buffer is cleared to 0. of a size 431 bytes. And keep in mind that the actual valid size of the packet is actually 164 bytes. So it's not 431 bytes as per the buffer size. It is 164 bytes only. And to calculate the size, it uses the following equation, I should say. So first, it gets the length of the URI file name. In this case, it would be length.php, followed by this hard-coded constant, which is 0x90, and then followed by the length of p key. Oh, interesting. At least in this calculation, he is accounting only for the string p key, but not when it comes to parsing the actual payload. And then it gets the length of the domain name, and here I'm translating it to the same size of the domain that is used with the malware, but it's just a fictional name. And then followed by the addition of 104 hex by y, 104, why there's your x90, I have no idea why. And then it comes to a total of 431 bytes, which is exactly the size of the buffer on the heap. But this does not match the actual size of the packet. So you might be wondering if this is a deliberate mistake or a non-deliberate mistake. Honestly, it is a non-deliberate mistake, and this is a blatant mistake by the author, because the content length value is set to 4, and the payload honestly is supposed to hold only the value p key without the rest of the zeros. But in this case, the malware was using the WinSock library, and it uses the send API function. So in this case, no library would complain about sending such requests to the server. So yeah, this is what happened in this case. And unfortunately, at the time of when testing this request, like with the actual malicious domain, the server wasn't alive at that time to confirm this hypothesis, be it like a deliberate mistake or non-deliberate mistake. So this is one aspect of this anomaly in this request. And the other one is the missing of the user agent header field. Although it's not like an anomaly in its own, but you don't get to see that much of valid requests without the user agent field. This is just something to keep in mind when you want to mine for malicious traffic or any anomalous traffic on the network. So this is a p-key malware. Now we go into another interesting malware case, and this is quite interesting. And I'm also requesting additional insight from any of the attendees that are willing to provide in case they see it differently from what I see it. So I call it the reverse gear scenario. So first, you have a malware that's running on your infected system, right? And then it establishes a TCP connection with the server. And right after establishing that connection, the malware actually sends this request that's showing in this particular slide. Yes, you might be wondering, this is a server response. It's not a request-looking packet. No, this is what it sends. The malware sends this request to the server, but this looks like it's coming from the server, right? So for you, first of all, I'm pretty sure 100% that all of you would think this is a valid HTTP request. When you look at Wireshark, I mean, there is no denying that it's a valid HTTP request, irrespective of the directionality of this request, which still doesn't make sense. But let's go with the assumption that it's a valid and whatnot. And in the request itself, you see that the server is set to SFFE, which is literally Google web server. And then the content length to 53, and then your connection set to keep alive, and then you have the actual payload. So the payload is exclusive or encrypted. And yeah, I mean, here are a couple of other interesting things to keep in mind as well. You see that there is no comma between the header field name as well as the value. For example, the content length the value 53, like usually in normal traffic, typical traffic, you would see after the column, space followed by the value. The same goes for the connection keep alive header. It is not a violation of the specification when you see such syntax, but it is anomalous. That's all there is to it. So just keep that in mind when you want to, again, mine your network traffic looking for any abnormal traffic. Of course, here you can tell that the malware is trying to blend with Google Web Server traffic. But seriously, like if this malware was running on a corporate network and what? The corporate network is using Google Web Server and this request is originating from your corporate network with SFFE server, of course, it doesn't make sense. Again, in this particular scenario, the malware was using the WS232 library, and it uses the send and receive APIs. The other thing that you need to keep in mind in this scenario is that this entire request is actually hard-coded, of course, other than the payload. The payload, again, as I mentioned, contains a unique string, which is exclusive or encrypted with the key 77. So yeah, so after sending this request, again, remember this is a request, not a response. The server responds with this request, okay? It's actually not requesting anything from the malware. Although it's a GET request, but it's not requesting anything from the malware. Again, there are lots of anomalies in this request too. A GET that comes with a payload. Of course, you would expect a payload to be associated with a POST request, not a GET request. Again, this is not a violation of the RFC, but nonetheless, how often do you see a payload associated with a GET request in a legitimate benign traffic? Almost non-existent, almost. And the other anomaly is the host header is set to the loopback address. Seriously? So you have a malware CNC server sending a GET request to the malware itself with the host header set to the loopback address. Of course, it's just fake because at the time when you establish TCP connection, you use the actual correct malicious IP address, and all of this is totally irrelevant unless you're going through a proxy or whatnot, and then this becomes an important field. In this case, again, the payload is exclusive or encrypted with the same key, and it contains sort of a magic string. The coupled length value, surprising, is actually correct. What else can I say about this one? It is missing user agent header field. But yeah, this is it for this particular request. So again, remember, this is the server response, not the malware request. And just to give you an idea as why this might be confusing, because when the malware received this request from the server, it does not parse the HTTP request, despite what Wireshark is telling you that this is HTTP. It is actually only, it's exclusive ORing the entire payload, including the header and everything, because the exclusive OR is stream-based, and exclusive OR the entire payload, it's going to end up exclusive ORing the payload of the request, and having the full decrypted magic string. And then it does a string match looking for that magic string anywhere in the payload, which is a very silly way of having to do all of that. I mean, I understand that the malware is trying to blend with the rest of the legitimate traffic, but it's still. So again, this is a clear indication that we're not dealing with HTTP traffic at all, actually. The actual malware communication protocol is in the payload of these requests, in the request and the server response. So it has nothing to do with HTTP. HTTP are used only as a camouflaging mechanism, that's all. And for the untrained eye, this might go unnoticed for sure. So in this particular case, if you decide like you wanna, like how would you detect such anomaly on the wire, right? So you might ask yourself, like, what kind of signature would I write to detect this traffic? I mean, there are lots of indicators that you can account for, but generalizing such detection is not actually that simple without incurring lots of performance impact on whatever device you use, be it Snort or any other commercial product. So you have also to account for the net flow context in this particular case. So for example, going back to this request that is going to the server, I mean, you can enforce the directionality of the request with the server being like holding the value as FFFE. And if this is going back, like going outbound from your network, then of course it stands out and you should alert on it. At least it's the minimum you should do. I'm not going to focus on the detection aspect of the actual malware payload. This is very easy. It goes without saying. So this is that for the reverse gear case. And my request for the audience is, if you have any other insight as to why the malware, why the malware author would use such reverse directionality, please let me know if you have some other creative insight. So now we go into another malware known as Proton Bot. This is also another interesting case. And the specifics of this request is the content type header that is associated with a GET request. Sorry. But how so? Usually GET requests don't have content type. It is used to signal to the server what type of data it's being sent. So if I am posting data to the server, I am telling the server I'm posting X data with this content type. So expect this content type of the data that I'm sending. But in a GET request, what kind of content type data that I'm sending? As actually, as per the RFC, content type is used in a post or put request methods. And if it is used, if content type is used as part of the server response, it means that it is informing the agent, whoever is receiving this request, about the type of data that the server is sending. So again, it indicates the type of data that either I'm receiving or I'm sending. So if you try to load this PCAP with this particular HTTP packet, actually even Wireshark wouldn't be able to parse it correctly, and it will err on it because content type doesn't make sense in a GET request. So so this one is actually it is a semantic type error. It is a violation and shouldn't happen in legitimate traffic. So I mean, checking for such anomaly on your network is easy, but again, you're gonna have to keep in mind the performance impact of whatever signature you're writing, especially if you're doing these things in real time. So you could easily check, for example, for the presence of the content type header in any request method other than put or post. Again, you can use these performance intense signature for data mining, for example. You don't care much about performance since it's not in real time. So it's still valid to generalize your detection methods. So this is for Proton bot case. Now we'll move into another malware case. This is what I call the crosswalk case. And this one is a bit interesting, and it is based on my own interpretation of what is the likelihood, the cause of this error, and what infliction it might cause should you be attempting to parse the server response on your own. The issue with this particular case is the value of the content length header in the server response. So first, you see the malware sending this GET request with the custom header, again, custom header, DCY. This is custom header, and then there's nothing wrong with that. Remember, back in the days, custom header has to start with the characters X uppercase, that followed by dash, followed by the custom header name. This was dropped later on, and then it became that you can come up with whatever a custom header name you want. It did not follow any specific standardization other than the specifics of the other headers have to follow. So it became even more difficult to fingerprint custom headers from legitimate headers, unless you want to look for like whitelisting or blacklisting stuff. But that's also very expensive. And in the GET request, you see the content length header with a value of 0. I've seen this many times, actually. It's very surprising to see it, actually. It's just waste of space. And I mean, I'm not sending anything. There is no payload associated with the GET request. Why do I even have to use this header? There is no point of using it at all, especially if it has a value of 0. And I've seen it like in malware and legitimate applications too. So it's probably that, like for example, in the case of legitimate application, that whoever is implementing such request doesn't know what he's doing, he or she. So that's that. But here, just to mention, in the custom header, this is how the malware is exfiltrating data. It is base64 encoded, as you can tell. So after sending such request, the server responds with this response with these headers. Now, what stands out the most, of course, is the content length value. I mean, of course, it doesn't make sense at all. Like the value, this is in bytes. In megabytes, this is like about 524 megabyte. The actual payload in the server response actually is only 256 bytes. Yet the content length value is such value, such very huge value. So you might ask yourself, but why? How such discrepancy? Like, what happened? What went wrong here? Again, just keep in mind, going back to the library things on Windows. So the malware is not using any HTTP library, actually. It is the WinSock. And yep, it's using the WinSock library. And sorry about that. So yeah, the WinSock library. And for receiving such requests, it uses the function receive. So it's not using any HTTP library that will parse the content length header, gets the value, and then allocates a buffer on the heap with that value, and then moves the actual payload into that buffer. So the malware itself is not vulnerable to such mistake, actually. It is the malware analyst or malware researcher or whatnot, whatever you want to call it, who is vulnerable to this. Because if you're trying to automate some milking processes, like if you want to send these requests by yourself to the server and expecting something in return, like you want to milk like the server response at specific point in time, you want to automate this process or whatnot. So usually this is how you would do it, like in a standardized fashion. You would use some HTTP library or even your own parsing mechanism. You go to the content length, get the value, allocate a buffer on the heap, and then get the payload. So if you attempting to allocate such buffer like multiple times within the same process, you might run out actually of memory on your system. Now, if this is a blunder, or is it an intended mistake? I don't know. I'm actually puzzled as to why this is happening. But this is something to keep in mind. And again, how would you detect such anomaly on the network? It's the same as with the other case that I talked about previously, when the content length value doesn't match the payload in the request, but here it is in the server response. So you can check for the value and you can check the payload as well and see if the length matches or not. Again, this is expensive because there is nothing unique that you're accounting for in your signature. But for data mining, this is gold. So keep that in mind. Now we go into another malware case, which is also interesting, just like the rest of the cases. And what's interesting about this one is the use of illegal characters in a given header name And in this case, it happened to be the connection header with the value close. You can see here we have the value open parentheses followed by the string null followed by the closing parentheses. So this is a violation of the RFC actually. This is not allowed. A header field name should not contain illegal characters. You might be surprising from what I'm about to say that in this particular case, when the malware sent this request to the server was running Apache version 2, and the server did respond actually with the status code 200 OK. So how come? If this header is a violation of the RFC, yet the server just happily accepted this request and responded with 200 OK. When I tested this request myself, I mean, just taking like this anomaly into consideration and sending it to the latest version of Apache, all locally, of course, not to the malware server. Actually, the server did reject this request, and I got back a 400 bad request status code. So this means that it's either a modified version on the like as a part of the malware backend server, although it's the same server like Apache, but it's a different version, or he relaxed some of the restrictions when configuring the server. Testing the same request on Nginx web server, I also get back actually, surprisingly, Nginx server does not inspect any header for such anomalies. So you could have this illegal character anywhere in any of the headers, and Nginx will still happily accept the request and not complaining at all. We'll go later on, hopefully in the next slide, I suppose, as to why this is happening, why this discrepancy between different servers. Again, detecting such requests, like in terms of generalizing the detection, might not be easy without incurring a lot of performance impact, but you can check for the presence of any illegal characters in the header field name. And you can get the list of illegal characters from the RFC specifications. Speaking of illegal characters, Socknet is not the only malware that committed such a mistake. We also have these two additional malware families known as Cobra and iTalk. In the first case, we see white spaces at the end of every line in the HTTP request, starting even from the HTTP method line, all the way to the HTTP version, followed by the rest of the headers. So you see a space character at the end of every header, or every line in the request, I should say. To send this request, the malware uses the OneSock library, and it uses the send function. So again, it's not using any particular HTTP library. Just so you know, in this case, the malware is actually exfiltrating data through the cookie. This is irrelevant to the talk, but just so you know. And at the time of testing this request, the server actually wasn't responding, so I didn't get to see what the server would respond to such request. But I doubted that the server is HTTP compliant. Probably it consists like of a custom HTTP parser or whatnot, because all it cares about is the cookie header that it would parse and get whatever exfiltrated data that it's looking for. Now, I tested the same request against Nginx with these white spaces. Again, it returned a 200 OK status code. So it happily accepted such request. Whereas in the case of Apache server, actually the server rejected it with the 400 status code. Exclusively if the white space is after the protocol version number, like on the as shown in the, on the first line. So for Apache, if you have white space character at the end of the first line, it will be rejected. So it all depends on the stringiness of the parsing of the request. In the case of ITAC, the second request, there are lots of anomalies actually. Again, you see the connection preceded with the white space illegal character. And surprisingly, again, this request was accepted by the server and didn't complain about it at all. But what is interesting is that this GET request also sends the payload, which has a value of 00 in hex, and there is no content length header associated with this request. You might be wondering why, because I have no clue why. So this could be like a blunder. It's not an intended mistake or whatever. But all of these help us into detecting this traffic, because otherwise, if it wasn't for these blunders, like there is nothing unique about the request that would allow us to detect it in a blocking fashion. And actually, a similar case was outlined by Fox at MT when it comes to the white spaces. Fox at Intel, they talked about a particular version of Cobalt Strike server known as Nano HTTPD, used in Java servers, whereby there is an extraneous space right after the status code in the server response. And that's how they managed to fingerprint all active Cobalt Strike server on the internet. So they scanned all the IPv4 addresses, and they managed to identify all of the active Cobalt Strike servers. Because of this unique abnormality in the server response, that is a space right after the HTTP status code. So this is how you could leverage such mistakes to your advantage. Now we go into another case, which is what I call the mysterious case of Cloaca. Again, this is another similar one to the white spaces one. But here, it's not at the beginning of the header field name. It is at the end of it. Now, what's interesting here is that other than that white space is an illegal character, it is the fact that you're not allowed to have a space between the header field value and the column. This is also a violation as per the RFC. So here you have even an illegal character. Actually, it doesn't matter anymore because it's an illegal character which supersedes any other violations, like in terms of order of parsing. As you can see in the host header, and you can see the other anomaly is in the accept header. There is no accept open parentheses dash encoding closing parentheses header, like as part of a custom header. Of course, this is a blatant mistake, or probably whoever wrote this malware doesn't know what he or she is doing. And yet, again, just to mention, as per the RFC, no white space is allowed between the header field name and column. Like, this is verbatim copy from the RFC. It's not my own wording. And as per the RFC, sending such request, the server must reject it with a response code of 400, meaning a bad request. And why? Like, why would the RFC enforce such restriction? It is all for security purposes. And I'm not sure if you remember, like the CVE 2019-16276 in the Go HTTP library known as Net HTTP. And actually, it's a similar case, and they end up with the CVE. You can look it up and read about it. So those mistakes there could turn into some serious vulnerabilities. They look sort of how to say it, not too severe. It's just a space after the header field name, but the implications are very severe, actually, of course, depending on the context or whatnot. And another thing to note here, that Cloaca actually constructs this request manually, And it uses the socket library, so no HTTP library, to send this request. Again, surprisingly, the server accepted this request without any complaint at all. And for this particular case, the server was running Apache with PHP version 5.3.28. How did that happen? I have no clue. But again, we will see later on what could be the reason of these servers accepting these requests without any complaint. And in case you want to know why, it's all going to come to you in the next slide. And so what would be the reason for accepting or rejecting a request that does not adhere to the specification, like even if you are committing some serious mistakes in the request? It all goes to what's known as the robustness principle, which is clearly specified in the RFC 2145. And it says, in general, an implementation must be conservative in its sending behavior, okay, and liberal in its receiving behavior. Aha, so this explains it, technically speaking. It must be liberal in its receiving behavior. That is, it must be careful to send well-formed datagrams, but must accept any datagram that it can interpret. So it's going to keep parsing whatever it accepts, not object to technical errors where the meaning is still clear. Aha, so this EG actually clearly mentioned that as long as going to still accept the request as it is. This is not going to have any unintended consequences, apparently. Of course, this is implementation and interpretation dependent, whereby different HTTP servers did not behave the same way. So as you can see, this is not mathematical equation. This is English language, meaning that if I'm implementing an HTTP server myself, I could interpret the same thing differently from another person implementing the same specifications, and have fun enforcing such a standard. I mean, even implementing a compiler with like C++ with a very, very strict RFC, you still end up with unintended consequences. Yet it is a compiler. So how about implementing a protocol like HTTP, which is text-based, and it's not math? So this is what could go wrong, technically speaking. It's up to the implementer. It depends on his mood. It could be, I don't know. So here we go into some more generalized mistakes, more interesting ones too. First, I talk about the many cases of malware accept header blunders. So the accept header, when you see it in a request, it's literally meant to signal to the server what content type the client is able to understand. So when I send a request to the server, be it a get request, for example, and I have this accept with whatever value that it takes, I'm telling the server that this is the type of data I'm expecting from you. I cannot accept anything else. Of course, it depends on whatever accept value that is specifying in the request. And the accept header value has this syntax. This is not my own syntax. This is as per RFC. So first you have the mem type, followed by /, followed by the subtype. Or you have mem type, followed by /, followed by anything, so any subtype. Or you could have any mem type, followed by /, followed by any subtype. So you have these three combinations only, okay? And the mem type and the subtypes, they're already listed in the specifications. So you can have a whitelist of all the possible values that these types could take. So what I did is as simple as follows. I checked for the absence of the / in the accept header field against 2769 packet captures. They are all malicious, all malware packet captures. And what I ended up with is the identification of 18 malware families that lacks the / in the accept header. So some of them, they were empty. Like the accept header has 0 value. Others, they have the value XML, just on its own XML. Another is you have the anything followed by dot, not / followed by dot. And one of them has a domain name in it. And one of them, nonsense value, like nonsensical, completely irrelevant value, like binary type value. That doesn't make sense at all. So I only checked for the absence of the / which has to exist as per the syntax and the specification. And I ended up identifying 18 malware families. So this means that I was able to fingerprint malicious traffic, malicious between double quotes, without looking for any unique or specific malware traffic. So this is the power of checking for any abnormalities at the protocol level, syntax / semantic level. Of course, you can generalize such detection. It will not be only the absence of the / and I'm pretty sure you will come up with different results, even better results. But this is just an example to illustrate what you could do to detect anomalous traffic on your network. Of course, we're gonna keep talking about accept headers because apparently it's one not to be missed, and malware also seems to like to make mistakes in this header a lot. I don't know why. What's so unique about it? So you have this another malware. This malware is actually used in a targeted attack against some Vietnamese entities. And it arrives via the exploitation of a given vulnerability in a Microsoft Office document. The request itself is not filterable. There is nothing unique about the request as it stands from a data perspective, meaning like the payload is dynamically generated by the malware via the call of create the GUID. So just create a unique ID on the affected system and sends it out. The content length value is correct, and nothing else. The user agent value is correct. I mean, it's a standard. There's nothing unique about it. Even the URL is very benign. What stands out is the accept header, which is quite an interesting mistake. So here you see the xm.plication. There is no such value in the accept header, like as part of the specification. So it's clearly a mistake. How did the author commit such mistake? I have no clue. They probably deleted, erased some stuff while coding this request. The actual correct value should be this one, XML followed by comma followed by application. So this is how you would detect this request. Actually, this is the only way you could detect this request. So this is another blunder. Now we go into another header, the cookie header. Its oddities and peculiarities. We must have all seen the cookie header used in so many different ways. And its use is known that it's used for tracking, session management, or customization. So every time you log in into some server, rest assured, most likely the cookie is involved. And usually it is requested by the server via the set cookie header to store whatever cookie on the client side, whether it is for tracking you, I mean, from privacy perspective, or for storing whatever data for later retrieval. And it has the following syntax. This is as per RC as well. You have cookie header name, followed by this key value pairs, followed by the semicolon, followed by space, followed by other key value pairs, and so on. You can have as many as you want. Now remember, the separation between the key value pairs is semicolon, followed by space. So out of curiosity, see if any malware would deviate from such syntax. I checked for the absence of the separator equal, like that separates the key from the value. And to my surprise, after checking the same set of PCAPs as in the previous case, I ended up with the following. That is the identification of additional 13 malware families, whereby 9 of them have 0 cookie header value, nothing at all. 1 of them has spaces, and 3 of them were exfiltrating data through the cookie header. This is just by checking for the absence of the equal character. And in the same case, I checked for the pair separator, that is the semicolon, such that it's not followed by space. And in this case, I got like in my data set, I was able to fingerprint this malware family known as NuBot, which is not part of the original data set, which exfiltrate data via the cookie header actually. Now, you might say, this is not too malicious, the check for the semicolon such that it's not followed by space. It's funny, the specification clearly says this is how we should code it, and this is how we should parse it. But of course, you will get to see actually some of the same violation in the the semicolon and the next key value pairs. But nonetheless, just keep in mind in case you're mining your own network traffic. Another interesting cookie and some other header mistakes is in this malware family known as Cepnet, which is an old malware family. I don't think it's selective at all, actually. But for documentation purposes, it's still interesting to talk about it. And of course, as you can see here, what stands out the most is, again, the cookie, which literally ends, like holds this hexadecimal value and ends with a dot, which is interesting, a dot. Of course, I mean, this is obviously something stands out here, and you should be suspicious of this request when you see it on your network. The other observation in this request is the content length value. As you can see here, the payload is 00 without the CRLF separator, which you should have 2 as per the specification to separate the headers from the payload. But here, there is only 1. So there's another major violation. And of course, the value does not match the size of the payload. Again, we have been through this before in the other cases. This is also a clear violation. And then you have the more blatant mistake, that is the use of the max forwards header with this very large value. So the max forwards header is actually used with either of the HTTP methods, trace or options, and it not a GET request. And it is literally used for limiting the number of forwards the proxies have to carry. Of course, can you imagine this request going through a proxy? And that many number of proxies, 107,000, 1900 proxies until it reaches its destination. Of course, this value does not represent the intended meaning of, or does not hold the intended meaning of this header. It is actually a dynamically generated value by the malware, which is used for like signaling to the server that, hey, this is the port that I'll be using for listening. So this malware is telling the server that this is the port I'll be using for listening for any other coming messages when it opens another TCP channel. And of course, as you must have figured out already, this request won't be parsed correctly by Wireshark because lots of violations in this case. And again, this request was sent by the WS232 library using the send API. And it uses the receive function to receive whatever it's expecting from the server. So no HTTP library was used in this particular case. So I'm just taking a sip of water. Now we'll move into another case, what I call silencing silence. Well, silence is the name of the malware, which is also known as TrueBot. And this one again is, I mean, it's very obvious just by looking at the packet, like the TCP stream, and it's in ASCII format, and you can tell that the user agent value holds the value of 2 lines. Yeah, it doesn't make sense. Of course, it doesn't make sense. You can see it in the hexdump as well as in the ASCII stream. You can see that 0D0A as part of the user agent header value. Now recall that for HTTP 1.1 version, the request has to at least hold the header host for it to be valid and accepted by the server. Again, it really depends on how the developer interpret the specifications and whether it allows such requests or not. But as per the specification for version 1.1, the GET request has to have at least the host header. But as you can tell here, it does not have the host header. It does exist in the request, but when you send this request and the server receives it, what it's going to see is the first line, the user agent with empty value, and then it's going to take the host and the connection header as part of the payload, and not part of the header request because of the 0D0A, 0D0A separation. And yet, in this case, I don't know if the server accepted this request or not, because at the time of testing this request to the actual malicious server, the server wasn't alive to verify this hypothesis. But it should definitely be rejected nonetheless. And of course, loading this with a Wireshark, Wireshark would complain about it, of course, with the message, leading CRLF previous messages in the stream may have extra CRLF. This is actually not enough of an error. There are other major problems with this request. But this, you can see that malware authors sometimes sort of innovate when making such mistakes. So it's not only in the accept header, but any header. And in case you're wondering, how did they end up with this mistake? You can see it here in the slide. So, I mean, the malware uses the Windows HTTP services, the Win HTTP library for sending this request. And to initialize the Win HTTP functions and returns like an HTTP session handle, it calls this API, the Win HTTP open, which takes the like the value of different headers. And in this case, we can see that the user agent header is taking the double new line value. So the mistake is very obvious in the code. Looks like not only senior engineers don't code edit their code, even malware authors don't edit their code. So this one is actually, I think this is important. And it's a statistical analysis on the same set of PCAPs, the 2769 malicious / malware PCAPs, looking for different anomalies in the user agent header, and see if we can come up or identify malware that deviates from the norm, at least. So in the first case, what I did is I checked for the presence of the plus character in the user agent header value. And to my surprise, I got back 15 malware families. So all of them that use HTTP traffic, they use the plus character in the HTTP user agent. I mean, yes, you can say that it is not malicious on its own because sometimes it is substituted for space characters instead, and it's a user agent header value. You can also sort of innovate on what characters you use in this header because it's supposed to hold the name of the client that's making the request. So it's not unique in any form or shape as per the RFC. There is no whitelisting list. And I mean, this exception that I'm talking about is you have this the malware family known as Bestafera, which uses actually the Googlebot user agent value. And as you can see, you have the leading plus character for the Google domain URL. The other test that I did is to check for the ampersand in the user agent header value. Again, I got this Allurian malware family, and you can see the value that it actually holds, which looks like, or not looks like, it is actually the case that these are HTTP parameters. So you would expect to see this in the URI, not in the user agent. So this is a very easy way to identify such anomaly. And again, Danbot, which was also found by SecureWorks, also committed such very similar mistake as well, where the reference, the ampersand was found in the user agent header value. The third case is the presence of the equal character in the user agent header value. And I ended up with the identification of 8 additional malware families. And all of them happen to be exfiltrating data in the user agent header, except for one. It's still malicious, but the mistake is quite funny, which, as you can tell here, there is a repetition of the user agent header field twice, followed by equal instead of column, which is nice. So this is another way to identify this request on the network. The fourth case is checking for the backslash in the user agent. Again, I ended up with 7 malware families. So just checking for these, I mean, they need not be called illegal characters as much as non-common characters and legitimate user agent values, or at least known user agent values. I mean, of course, you can come up with your own character, or it depends on your creativity or whatever you can come up with looking for anything anomalous in these headers. So this is just an example, just to give you an idea of how you can fingerprint anomalous traffic, be it for specific malware family or any other type of malicious components on your network without having any specific signature. So such detection outlive any other malware signature because it's very generalized and it targets the syntax or the semantics of the protocol itself. I wasn't happy enough with the user agent. So I said, okay, so let me check for other HTTP headers that do not use commonly used characters. And in this case, I checked for the content disposition header. Usually this header takes either of the values: inline, attachment, form data, or name or file name. So what I did, I just checked I mean, I parsed it correctly, and then looking for any value other than any of these RFC defined values. And again, I got this malware known as Nalodu. And as you can see here in the request, it is holding a value that doesn't make much sense, which is clearly like some sort of identifier used by the malware. So yeah, and as you can tell here again, the user agent holds computer-specific information, meaning the malware is exfiltrating data through the user agent header. These checks, they are very easy to implement, except for the fact that they are very performance intensive. But for data mining, they are very good. Now, this presentation wouldn't be complete, actually, at all, without spotting an actual corrective, what I call corrective mistake in the referrer header. As you might be familiar already, the referrer, like the word referrer in the HTTP protocol is used in the wrong fashion. I mean, it's used with one R, and if in case you are interested about the etymology of how did this end up in the HTTP RFC with the wrong word, not with the double R, please look it up on Wikipedia. But suffice to say that this ultralocker malware family used it in the correct form as per the English language, not the RFC specifications, and it used it with double R. So this is just to, I just wanted to mention this. Of course, you can detect this as something suspicious on your network. But interesting to see that somebody committed this mistake, actually. They are adamant that it has to be double R. It cannot be one R. So yeah. And surprisingly, just a bit of statistics here. So only 8 out of 276 malware families actually have the referrer header field in their request. I'm actually surprised because to blend with the rest of the normal traffic on your network, malware also, they should actually use the referrer header, but it's sort of like legitimize even further the HTTP request. And some other interesting checks that you can do yourself as well is checking for the case sensitivity. Again, this is not a violation of the RFC, like whether the header is uppercase, lowercase, or whatnot. But in normal traffic, there is sort of like standard that everyone follows. That is, the first character is uppercase, and then what follows is lowercase. I mean, if you've looked at enough network traffic, you can clearly see it. So what I did, just to see if I can spot anything interesting in the same set of malware PCAPs, I literally checked for the case sensitivity of these list of headers, such that they are all in lowercase. So if I had to check for the Pragam, it should be Pragma, I get 6 malware families. And the same thing goes for the rest of the headers. I mean, just for cache control, all lowercase, I get 9. Now they use it. Now here, keep in mind, for the user agent, actually the libsfml library. I mean, it's a very famous library for if you want to write like that. It's for writing games, but it comes with the network module and the file system module and the sound module and whatnot. It actually has all of these header hard-coded, and they're all written in lowercase. So it's not just by seeing a lowercase the headers, it means the traffic is suspicious. But it's just something to keep in mind, especially when you want to take this into consideration in addition to something else, and then tie all of these together and then come to a verdict whether the request is malicious or not. And yeah, I mean here, The other thing that stands out is the content disposition. I get 10. And surprisingly, just checking by the lowercase, I found a family that was actually sending control commands via the content disposition header in the request and the response. The other one, in the endeavor of checking for sensitivity in the request, that is, I checked for the get method such that it's all lowercase. And surprisingly, I get two malware family that uses it in it is lowercase format. Whereas for the post case, I got 0. This just like statistical stuff, but it's something to keep in mind again. And the other one is I checked for the HTTP string in the request. Like when you send a GET request or any HTTP request, you have the HTTP followed by the version number, right? So I checked for it such that it's all lowercase. And funnily enough, I was able to identify this blue summer malware family. Like the rest of the request, they use standard capitalization, except for the HTTP string in the request. And the other anomaly is the use of this accept header that uses the value HS-UK, which actually is not part of the specification. So I'm not sure from where did the author came up with this value. The other thing that you can check for is the zero spacing. Sorry, I should mention this just to show it. The zero spacing between the column and the value of the header. Again, I mean, it's not a violation, but it's just something to keep in mind. And again, like you can see here in this request, you can see like the comma. I mean, it's not that it's a violation again, but it does separate both values, but you would expect it to come right after the first value and then followed by deflate. But just something to keep in mind. It's not that hard to generalize the detection for these anomalies at all, actually. After going through the paper yourself, you can come up with whatever signatures. I talked about empty headers, like when I talk about some of those statistical analysis. But I will revisit it in the next slide, and you'll see that we have the malware family known as B-Rich, which used in limited targeted attacks, and it was delivered via this vulnerability. I think it's Internet Explorer vulnerability. So this is a targeted attack, so we'd expect that the threat actor is a very articulate and meticulous in terms of coding, interacting with the server, and having everything adhere to the specification or whatnot. But it's not the case actually. And surprisingly, you get to see like these empty headers, like the accept encoding header has an empty value, for example, right? Why? I don't know. It's just, it is what it is. It's just a blatant mistake. So you can easily check for that to fingerprint such anomaly on the network. Now we're done with all the cases. I'm just here. Sorry, I'm losing my voice. Just some other consideration that you should keep in mind, and it's some of the stuff that I try to play with to see what other anomalies that I can identify in some of the available public source servers. For example, if you send some request against Nginx or Apache with an HTTP version other than like 0.9, 1.1, or 2, in case you're upgrading your HTTP request, actually the server does accept the request just happily. I'm not sure if, are you guys aware of HTTP version 8, version 15? And so I'm not sure why would they accept this request. I don't know, but it's just something like I found surprising. And the other thing that you have to keep in mind when writing these or checking for these anomalies is that you have to be port agnostic. this goes back to my pain point at the beginning of the presentation. If protocol is never defined by its port number, so should your signature. And again, as you can see, implementation is still a subjective interpretation. If I wake up one morning, I don't have my coffee, and I want to implement some feature, I'm sure it's going to affect my own understanding of that language paragraph, like that English language paragraph. And case in point, I'm sure you must have heard of the HTTP request smuggling attacks, which actually could illustrate what could go wrong in case the developer of the HTTP specification does not clearly understand what the specification says. And you can end up with some serious implications in terms of vulnerabilities. And like the first request smuggling research was carried out in 2005 by Watchfire, and then an additional research was carried out recently by Portswigger in 2019, and they are still actually doing additional research on it. Like every now and then they come up with additional blog posts that illustrate this case. And so yeah, this is something to keep in mind, and I recommend that you read over this request smuggling reborn attack, because this is clearly a case that needs attention from everyone in the industry, actually, of how everyone interprets the specification when it comes to the implementation. That's why it seems that the English language is harder than advanced mathematics. I guess that's all. I've got nothing else to share or say, and I hope you enjoyed this talk. It was informative, or
yeah, it was really good.
Interesting. And for conclusion, as usual, I don't give conclusion. I leave it to the audience to come up with their own conclusion. And that's all from me. And thank you.
Well, thanks for you and your presentation.
Thank you.
So in the paper or anything, like do you have like a set of grammars, sort of like a compilation of your conclusion from all those like signatures that you identified from packets, you know, like I don't know, like signature for like PCAPs or like all those things? Did you manage to compile everything as like a tool or some like signature format? I'm not sure what people use for like network detection. What's the equivalent of VRR rules, you know? But I would assume there is an equivalent.
Exactly. I actually, in the paper, I do have all of these packet captures, and I have a conclusion, and I do mention the MD5 hashes of all of the malware that I talked about. However, I do not share the PCAPs nor any tool publicly.
Okay.
Why? I mean, the standard tool in the industry, like the open source tool, is Snort for natural detection. Like you can write your own Snort signature for detecting such anomalies. It's very easy. However, the reason why I didn't publish anything publicly is Snort is the standard one, but there are lots of other commercial vendors that have their own language different from Snort.
Yeah.
So that's why I leave it to everyone's understanding to come up with their own sort of rules and implement it in their own devices.
Yeah. No, that makes sense. I didn't realize that there were like so many different formats.
Yeah.
And we got a question from the chat, which was asking, do common proxy or URL filters protect against such exfiltration?
I'm sorry, say that again.
Do like common proxy or URL filters protect against such exfiltrations?
Oh, well, if the proxy is 100% adhering to the RC specification, then it might reject such request.
Mm-hmm.
So it all depends on the implementation that the proxy has.
Yeah, it may reject some stuff and may let some other stuff to pass. Basically, right?
Exactly. I mean, and also, you can. I mean, we all know that proxy is a very important tool, like for filtering HTTP traffic. And you can either write signature that would check for some of these anomalies, but it really depends on the order of evaluation when it comes to the proxy receiving the request and parsing it. So I believe it is proxy vendor specific, like when it comes to evaluating these things. So I can't generalize my answer.
Okay. Yeah, I think that's it. I already put your slides and the white paper you sent me on GitHub. Actually, I was just showing it on the screen now for the audience.
Awesome.
I don't think we have more questions. So, any last words to conclude?
That's all. I'll also be like publishing on my website, like the slides and the paper. And other than that, well, thanks again for the opportunity to present our opcode, and I hope everyone enjoyed it and learned something from it. That's all.
Yeah, definitely. Yeah, thanks again for coming. Take
Thank
care.
you.
Bye.
Thanks. Bye. Bye.